Alright, so carbon monoxide reacts with carbon monoxide, reacts with H2O to produce CO2 and H2. And these are all assumed to be gaseous because it doesn't say solid or anything else. Equilibrium constant is 5, so K is equal to 5.10. Calculate equilibrium concentrations of all species if 1 mole of each compound is mixed in a 1 liter flask. So, Kirk, you said set up the K expression. Can you go ahead and see what that is?
It's the concentration of CO2.
Okay, I'm sorry. I'm just making sure I'm balanced, right? I am, right?
Yeah.
Okay. Concentration of CO2
After concentration of H2.
over.
Concentration of CO and concentration of water.
Wonderful. Okay, and then you guys think we said start with the ice or rice box. Levi, what do I put for all of these? So 1 molar, right? Because that's 1 mole divided by 1 liter, so that makes it not quite easy. Okay, so I've set up enough to kind of get myself in the right track. But what do I have to do next, Sean? When you say favorite, I think you want to say a different word. Which way? What do you mean by that?
So since the KI is more than one, the products.
So the products to be favored, meaning I have higher concentrations of them at the end of the experiment. But I'm looking for something a little bit related to that, but not quite that. AJ? So we're going to look for Q and compare the Q to the K to see which way it proceeds, right? The word proceeds, we're seeing which direction it proceeds. So when I calculate Q, it's pretty easy. It's going to be Q is equal to all of this mess, but with our 1's in there. So 1 times 1 over 1 times 1 is 1. Okay, so I didn't show my plugging in of that, but I would expect you would. And then down below you would say Q is less than K. So what's my problem here? I have too few what? Too few products, because I need my numerator to get higher, so I need to add products. So which way is this proceeding?
Right.
Proceeding towards the right, towards the product. So I'm making products and I'm subtracting reactants. True? Yes? Okay, so subtracting, so I'm going to say proceeds right, so that we all remember that, okay? And subtracting what from the reactants? X and adding X and X. So it just happens to be a 1 to 1 to 1 to 1 ratio. And then we have 1 minus X, 1 minus X, 1 plus X, and 1 plus X. Okay, so then how do I set this up to solve for X? Okay, so you're going to go ahead and square root. I'm going to set up the beginning of that. So he said K is equal to 5.10. And now when you plug your values into your K expression like we have up there on the top, it's 1 plus X squared over 1 minus X. So products of reactants, right, squared. You got that so far? And then we said, so Levi said square root the whole thing, basically. What's the square root of 5.0? Say again? Sorry, I just need more space. Say it one more time. 2.25, and that's 1 plus X over 1 minus X. How do I then accumulate my X's and then go forward? So give me some steps here, people. Thank you.
So I moved 2.25 to the
Denominator?
I put it in my calculator like it was solver.
Okay, so you did solver, so you just subtracted 2.25 and then set it equal to 0. Okay, so you could do that, but mathematically, so give me some algebra, what next step would I do? AJ? Okay, so when you multiply and you distribute, then we eventually get to 2.25 times 1 minus X equals 1 plus X, and then distribute in, and then 1 comes over, and then the X's get combined. Yes? I'm trying to give you some support, but there is a prereq for this class, and it's like Math 3, so I'm not going to baby you too much. 2.25 X is equal to 1 plus X. Well, if I'll write that out. And then negative or minus 1 over here, add your 2.25 over here, so 1.25 is equal to 3.25x. Yes? And then divide and solve. So what do we get for x?
3.4.38.
0.38. Can I get more?
6.
One more?
6.2.
6.2. Okay, so 6 again. So if once we solve for x, then we finally have x. So then what you should finally do for your final concentrations is just plug that in, your x value up here, into each of your x's in your equilibrium section, and then you'll have your final concentrations. Cool? Easy process if you have the perfect square root, which we did in this case. Now, what I'll do is I'm going to work on setting up, because I think mathematically, I don't need to support you too much here, but you can correct me if I'm wrong, okay? So on the next one, assume a reaction for the formation of gaseous hydrogen fluoride from hydrogen and chlorine has an equilibrium constant of blank. In a particular experiment, 3 moles of each solid plus calculate equilibrium concentrations of each species. How is this one different? K what? K is given actually. It says equilibrium constant of 1.15 times 10 to the second. Sorry. How's this one different? Yeah, the K is big. The first one was 5. This one's like 100, but it's big. Tell me that thinking further down in our steps, how's this one look different? Right, that first one did as well, but it was 1 and 1, so it was a really easy calculation. How about that balanced chemical equation? What's it look like? I heard H2 plus F2 yields or equilibrates 2F2 or 2F, 2 hydrofluoric acid or hydrogen fluorides. So that's going to cause our K value, our expression to have a squared in it, right? And when I do my ice box, I'm going to have a 2x in it as well. And we also, each component, so 3 moles of each component means all of them have an initial starting point. So what do I still have to do with Q? Calculate and compare, correct? Okay, so the only thing that's going to be different is when we set up our ice box, this will be what? 3 over 1.5 is 2 molar, 2 molar, 2 molar, and then we have to figure out which is going to, which way it's going to proceed. So I'll set up the K over here. K is equal to concentration of F, or HF squared over concentration of H2 times F2. So this is going to be 2 for, I'm going to calculate Q right here. 2 squared over 2 times 2. So what is Q here? 1 yet again, because 4 over 4 is 1. So K is greater than, or I'll do it the other way. Q is less than K. So we still proceed which way? Forward to the right to make more products, and the Q eventually gets up to what the K value should be. So we're still doing what here? Subtracting one of the x's, subtracting 1x and adding 2x. And so in the end, we're going to have actually still a perfect square root because we have squared for our product here. But when I plug it into my K expression, 115 is equal to 2 plus 2x squared for my product over 2 minus x squared for my reactants. You'll still do a perfect square. You'll still rearrange algebraically and solve for x. Give me a 2 thumbs up if you're okay with the finalization of that math. Okay, cool. Most of us are good there. All right, let me pause there for a moment. We have the whole idea of like, you have your K, you need to find Q, you need to compare, and then plug and solve. Looking back at the problem set, let me take some questions from those. Problem set. Which ones?
Number 2.
So I'm going through with my key right here so I can talk about this efficiently. So you guys had initially your 0.5 molar, and it gave you 0 both your products, so you've had to proceed towards the right. So as you proceed towards the right, you subtract reactants and add products. However, you were already basically told the information about the product, or about the amount left or at the equilibrium point, so 0.13. So if you're adding equal amounts of both of these, because the 1-to-1 ratio, you have 0.13, 0.13 there for both of them at equilibrium. And then this one, since we know how much was added to one side, we know how much is subtracted from the other side. However, the 2 there does impact that to make it doubly, so 2x, so 2 times 0.13. And then when you subtract and solve, you get 0.240 molar. And then at equilibrium, once your values are achieved, take your equilibrium values, plug them in your Kc value or Kc expression, and solve to be 0.29-ish, 0.293. Yeah. 5. What's the next one? 7. 9. 5, 7, 9. I heard 8 too, I think. 5 is this one, and I'm going to show you both ways on this one, okay? So let me zoom out just a tad here. So in 5, you were given a really small k value, so 10 to the negative 34th, right? So as you started that probably caught your eye at first, but as you were adding in your components, zero products, you must proceed towards the right. You add x, you minus 2x over here, and then you see your values are going to go into your k expression. Your k expression is then x squared over 2 minus 2x squared. You can still do the perfect square of that, and so I expect if you can do a perfect square, you will do a perfect square, and you will solve algebraically that way. It's only when we get to quadratic formula we're like, let me just try my solver, okay? So this is perfect square. Solving for it like this, so when you solve for x finally using your perfect square and then rearranging your algebraic expression, you should see x is approximately 3.578 times 10 to the negative 17. Give me 1 second, okay? So that's a really tiny number, but you can definitely solve that way. So, but what you probably thought when you saw your your very low k value is what? Neglect x. So approach x is so small it's approaching 0, which is probably true. And what we have here is a very small k value, so you know you're not going to basically make any products, like super small amounts of products, which is a true statement according to the first way I've solved it. But just to verify that, I'm going to show you the other way, which is our neglecting x. So k value is very small. You get to the point where you're plugging in the minus 2x here. You neglect x, so I show that approaching 0. So it makes the math so much easier. So 2 squared is on the bottom, x squared is on top. Multiply by 4 and then square the whole thing. You get 3.6 times 10 to the negative 17. Do you see how close that is to the first way I got? 3.6 times 10 to the negative 17, 3.578 times 10 to the negative 17. They both work out exactly the same. And so this is proof of concept. Neglecting x does work. And then I don't have my 5% rule shown on here, but what would I've done here? So take my x and divide it by, who was the smallest value I would have added or subtracted it from? 2, right, was the only thing I was adding and subtracting it from. So that divided by 2 times 100 is for sure less than 5%, because it's like 10 to the negative 17th, that's not even close. So it's like, yeah, something to the negative 15, or 10 to the negative 15%. So regardless though, this works for neglecting x, and then you plug in, resolve for your concentrations that it asks for. Alvin, what are you going to ask? Okay, cool. So I want to show you proof of concept, they both work. But if it's something algebraically, I think you should be able to achieve that. Just don't get in the habit of neglecting x all the time, especially if you're not checking your 5%. Because if you neglect x and the 5% doesn't work, you have to go back from scratch and start back again. Okay, so if the 5% doesn't work, you have too much margin of error, you can't make those assumptions, and then we have to go back to scratch. Okay, so that's 5. What else was I? 7? 7? Oh, this one had a solid in it, so in reference to your K value, K expression being solid, and gas, the K expression equaled only the concentration of CS2, so carbon disulfide. And so they gave you the initial of one of these, and it said this was an excess, which you're like, well, we haven't done it like that. And then the 9.4 molar being the final was your final part. But the K expression is only the concentration of that. So then you were, since that was equivalent, you were able to solve for the K. I'm sorry, you were able, since K was given as 9.40 and the K expression equaled the concentration of that, then that meant they were equivalent at equilibrium, so then you were able to put that in directly into equilibrium, the concentration of carbon disulfide at equilibrium. But the question wasn't, I don't believe, about the concentration, it was about the moles. So then you went back and the question stated it was a 5-liter container, so you take your molarity times your volume of container, you get 47 moles of carbon disulfide. So that was more about understanding the K constant was actually only equal to one thing. That gave you the power of plugging in just one value. Okay, and 8, 9, okay. So the first value, or this is the first time we saw partial pressure really. We've seen it like one or two examples in class, but not on homework. So the first part is, notice, and this is should be partial pressure. My bad. This is Kp, so whenever you write it out on your paper, it should be partial pressure of CO2 times partial pressure of water vapor, not concentration brackets, so just make sure that brackets are only for concentration. So whenever you plug in your Kp value, which is 0.25, excluding your solids here, the only two things are your two products, which are gases. At this point, you can see both of these as x, because they're made in a 1-to-1 mole ratio. So x squared is what your final Kp equals. And then when you square root the 0.25, you get 0.5 for your x value, which is your partial pressure. And most of the time, partial pressures are expressed in atmospheres. So that would then give you the opportunity to get the atmospheric pressure there. And then lastly, number 9, this was a KC-Kp relationship one. So our politically correct formula, given the fact that we have Kc already and the solid is excluded, the ammonia concentration and the hydrogen sulfide or hydrosulfuric acid concentrations are the only thing of importance. That's for the Kc though. And so for Kp, the expression is very similar. It's just P for partial pressure instead of concentration brackets only. So this is your expression. However, you're given the C value. So when you plug C value in, you plug the R constant for your universal gas law constant in there, and your temperature at 25 degrees Celsius, but in Kelvin is 298, as well as your delta N, which is products minus reactants. Moles of gas. It's just not moles in general, it's moles of gas. And so because we're talking about gases, you're only referring to gases. That's the reason why. So this is 2 moles of gas versus 0 moles of gas. So 2 minus 0 is 2. Plug it in and you get your Kp value to be 0.108. And then for the, I can't scroll down anymore, you might have to stand up, you can't see the very bottom. And once we had our Kp value and we saw that they were produced in a 1-to-1 mole ratio, that's making x and x amounts of both of them equally. So Kp is equal to x squared, square root Kp, you get the partial pressure of each of those gases, which is 0.329 atmospheres after you square root. And then you'll notice the final question, which is, this is a really good question, so I'm glad that whoever asked me for 9 is good. Once you get your partial pressures, if it asks for total pressure, you have to think back to Dalton's law, partial pressure plus partial pressure equals total pressure. So then your two pressures together, added together, is your PT, P total of 0.659 atmospheres. This is a good FRQ. You'll see something like this on your test. Okay, other questions right now? So one of my biggest misconceptions that my students always have is, because we're starting to see a lot of cumulative stuff now, most people think Kp is equal to P total. Kp is not even a pressure itself, right? What is Kp? It's an equilibrium constant and what does an equilibrium constant tell us? Okay, the ratio of products to reactants, but it also tells us what? Say again? Okay, so the formation of products are reverse reaction favored. It tells us the extent of the forward direction. The extent of a reaction has literally nothing to do with total pressure, right? It just doesn't. It really depends on, like, where are my gases at? You know, how much of each gas do I have? What size container do I have? There's a lot of other things that affect total pressure. So once we get to the part where we do know the partial pressures, then you can get total pressure, but Kp does not equal P total. Big misconception, because you're trying to get a lot of P's in your head now, okay? Okay, so can we switch modes here? Let's talk about lab real fast. Ready? So let me back up. Tell me what we're doing in our lab. You are. What's SCN called? Thiocyanate. Okay, thiocyanate. So we're adding iron 3 and potassium thiocyanate. And what's going to happen? Make a solution. Okay. Okay, so we're going to measure the concentrations how? Okay, so it's going to be measuring the absorbance and the color and there again. So as you can see, AP chemistry is just about color change. Just lots and lots of color change, guys. It just so happens there's a relationship between color and concentration, which makes us happy. So the one thing I'm not sure it said this color in the lab, but your, actually I think I have it right here, your color change that's going to occur is between iron 3 cyanide, iron 3 and potassium thiocyanate. Gosh, this is kind of a pale yellow. It's not too dark at all, and the colorless solution here comes together, makes like blood red. And so people do like Halloween demonstrations where it's really bad, but they'll put like some powdered thiocyanate on their arm, and then like have like a stir rod or a scapula and like accidentally like stab themselves, and then they'll have like iron on it, iron solution, and it makes it look like it's bleeding. I don't know, my students do that to me, and I was like, what's going on? He was like, it's just chemistry. Anderson Clark, anybody? Oh, thank you. So that was my nerd, like beyond belief, Anderson, he did that. Anyway, it makes a red color. So that's the color change you'll see. Red is a color that's opposite of blue on the color wheel. So it'll do, and normally I would have an absorbance graph for you guys like this, meaning like nanometers down here with the wavelengths and absorbance here. And I would say, oh guys, okay, here's the absorbance at different wavelengths. Let's see here, blue, so it's gonna like peak over here on this side. So this would be at like, what's blue's wavelength? 550-ish nanometers or so. So that's where you'll be looking at on your colorimeter for the absorbance level or the wavelength to select for your absorbance values. Okay? So, and you should have your concentrations already. Let me check this before you go back there. So, can I get some help on what your concentrations are? Pre-lab. First one.
Zero.
There should be work for this shown as well. It's not just up in your head. Why 0?
Because it gives it to you.
Okay, it gives it. Oh, sorry. The first one that's on that's a calculation. So number two. Number 2.
Like
8 times 10 to the -5. Why are you guys so like hesitant? If you're wrong, it's just us. No judging. You guys should be able to show your work for that. And then number 3, 1.2 times 10 to the -4. Next.
1.6 times 10 to the -4.
Next.
3 times 10 to the -4.
Okay, cool. All right. So don't forget, I'm actually, before you guys start prepping the solutions and such, your calorimeter needs to warm up some. I think that's been a problem with some of us. Immediately you're going to log into Logger Pro, plug it up, let that baby warm up. It's got to kind of like self-warm up so that the bulbs are bright enough to cause the correct absorption. Whenever you're using it, use the same cuvette, the little tiny box ones, same cuvette with the same face facing the detector, so that you don't have any extra error that could occur, because there could be different diffraction from the different sides of the cuvette. So you need to use a Sharpie to just make a mark on the face you're using. That might be helpful. And then be very, very precise, as always. A human error should never be an error point. Be as precise as you can so you have a good K value that you calculate in the end. Okay, so I'm going to put the samples, the solutions on the back, or maybe the front lab station, because I have some stuff for honors chem back there. You need your goggles on, and do everything on a piece of paper and on your pack that you have, which is the data tables and such, because I still have your lab notebooks, because you guys just finished Monday, so I haven't started grading them yet. All right? Oh, so, no, you guys can choose your lab groups. Let's do groups of 5, or, I'm sorry, 5 groups. 5 groups. Choose who you want. Let's go. I just got paid. I have 2 parameters. You guys suck. We have 2 jobs. I do have my job. 3 students, which I do.
I know this because it says so.
Nice job.
Guys, I know it's tempting. Please don't mess with the baby oil from honest now. I got baby oil.
Baby oil?
Do you remember the polar lab? That polar bear?
Polar. I said that today in class, and they're like, she's
Alright guys, let me give you some heads up on where materials are. So listen to me, 5, 4, 3, 2, 1, thank you. Yes, it says you small meters use a part. If you have to look around, there's more back here. These are the big request. The color pairs are here. Do you plug those in with your GoLink? I have a couple GoLinks here. There's also some food in the baskets for honors Chem. The thermometers, you can't plug up shoe probes in the same system. Unless you have, actually no, if you have enough GoLinks, you can do one thermal probe and one colorimeter. It will pull up both. So if you don't have enough, you can pull up both thermal probes. Thermal probes are already the baskets of honors Chem has been using them. Lastly, and then I'll let you go. The solution, what's the first solution you need? What's the solution you need? Concentration. 0.2 molar what? Iron trinitrate here, and then the second one is 0.002 molar. All five chlorinates. Okay, those are staying here. I'm going to take the rest of these. Guys, only take the solutions you need because I have a lot of groups and I don't have a lot of solutions. Guys, and I'm gonna be honest, just because the laptop, I mean, the desktops are working doesn't mean they're forever gonna work, so I would definitely start running laptops. Because you guys make these two right here, that's one that cut off. And then the circuit. Don't touch my baby oil.
Oh, okay, yeah.